Hello and welcome to this recorded e-learning on Spartan-3 HDL coding techniques. This module is one of the recommended recorded e-learning modules for the Designing for Performance course and is also a part of the FPGA to ASIC REL curriculum. My name is Frank Nelson. I will be your instructor for this module. I am a Xilinx technical trainer and course developer. This module introduces some of the architectural differences of Spartan-3 and their impact on HDL coding techniques. This module introduces some of the primary concepts that impact the quality of results a designer will get when synthesizing for a Spartan-3 FPGA. This module also provides some detailed recommendations about creating effective HDL that will provide high speed and reduce the amount of FPGA resources used in your design. This slide describes the curriculum path for ASIC designers to learn Xilinx software, hardware, and the FPGA design techniques. There are 5 RELs to help you get familiar with FPGA design. There is also a corresponding HDL coding techniques module for Spartan-3 devices, which you're listening to now, as well as one for Vertex 5. The content in this module will help you immediately start making coding improvements to your Spartan-3 FPGA design. There are 2 modules for Spartan-3 HDL coding techniques content. As I mentioned, this is part 2. For more information on these courses, visit support.xilinx.com and click on the education link at the top of the page. Also note that these RELs do not introduce the ISC design suite, good design practices, and other essential information. This content is part of our Fundamentals of FPGA Design course, currently being renamed the Essentials of FPGA Design course, as well as our Designing for Performance courses. We recommend that you take the time to attend these courses. After completing this module, you will be able to build an efficient Spartan-3 FPGA design that has an efficient size and runs at high speed. You will also be able to avoid the most common mistakes that new FPGA designers make. This content is essential if you have never coded a design for any 4-input LUT architecture or are converting an ASIC design. Our goal in this module is to take your basic knowledge from the last module and try to teach you some of the subtleties of the Spartan-3 FPGA device. To also teach you to pack the most logic into your FPGA sometimes takes some optimization of your code. Likewise, to get the required design speed sometimes takes further optimization. But often designers do not want or have to follow all the tips provided in this module, but they sometimes will need to. But in the end, we still recommend you probably start with these tips. As you probably know by now, synthesis tools do not allow inference of all FPGA resources. Sometimes good coding techniques are required just to get an optimum resource into your netlist. While the content in this module is not specific to a particular synthesis tool, or for that matter a particular 4-input LUT outside Spartan-3, and some of the tips have not been tested on all synthesis tools, this module does provide a good basis for experimenting with your synthesis tool. Now, this module is recommended content for the Designing for Performance course, as we mentioned. I recommend that you consider taking time to attend the class. And as I mentioned, this content in this module also applies to any 4-input LUT FPGA device family. This includes Vertex 4. There are corresponding RELs on Vertex 5 HDL coding techniques that discuss some of the issues with design conversion and proper coding for a 6-input LUT architecture. We are going to discuss some of the most important ways to optimize your HDL code for a Spartan-3 device. After listening to this entire module, you should be able to make your own checklist of design tips for building a high-speed Spartan-3 design. As you probably already know, the carry chain is used for arithmetic operations. The carry chain can be inferred easily enough by using your standard arithmetic operators. But what you may or may not know is that you cannot infer carry logic when you are using gates, such as the XOR gate to compute a half sum. In this case, the synthesis tool will not be able to infer the carry chain. You should also keep in mind that carry chains do not begin or end halfway through a slice, so it is most efficient to use the carry logic in pairs or an even number of bits. Otherwise, you may end up wasting resources in slices. Most customers don't spend any time comparing the carry logic implementation with other counter types. Using counters of any of these types can save resources or run even faster than a carry logic implementation, While these counters are not used very often, if you are running out of resources or having a timing critical path that passes through a carry chain, you might want to consider one of these other implementations. However, it will take extra time to construct one of these counters in your HDL. Binary counters are slow compared to the others, but requires the least amount of registers. It is also easy to simulate since it has a familiar count sequence. In fact, this is the one type of counter that most likely carry logic will actually be faster than. One-hot encoding is a faster implementation because it has less decode logic and uses more registers as you would expect. One-hot basically activates one register with each count. Johnson counters are ring counters. They are fast and use fewer registers than one-hot encoding, so they do have a bit of an advantage over one-hot. The LFSR counters are also fast and use fewer registers than one-hot encoding. The challenge with the LFSR counters is they use a pseudo-random sequence during the count, so they are harder to simulate and verify. As an FYI, you may want to use the plus and minus signs when building comparators. It will infer a fast implementation. While most synthesis tools don't give you a problem inferring carry logic in this way, you may want to keep in mind that by using these operators, the carry chain is used, and that should be a faster result. Building a decode function using gates can be very efficient and fast if you are using carry logic. The key is describing the decode behavior with an arithmetic operator so the carry logic can be inferred. We will see an example of this in the next slide. The challenge is that it requires a little more work and a bit of imagination to build. Finally, always use a case statement when decoding logic. This tends to synthesize to more of a parallel implementation, or parallel logic as we call it, and tends to run at a higher speed. But keep in mind that even if the logic is built in parallel, a carry logic implementation should be faster. In this implementation, a subtraction was used instead of a LUT implementation. As we mentioned, the benefit is that the carry chain is used and improves the speed of the comparator. As you can see, the greater than and less than signs are too ambiguous since they have to check for all possible conditions. This implies a lot of combinatorial logic since we are comparing two 7-bit buses in this example. But by instead using a simple subtraction, we get a more specific test of the bits on the bus, and this allows us to take advantage of the carry logic resources, which of course has that fast carry chain. The challenge is seeing the opportunity of using a subtraction rather than the old standby if-then behavior description. In this example, we see a decode function built with nested if-then statements. As we know, this infers priority encoders, which synthesizes to extra logic levels and can kill performance. The best solution is to use a case statement which synthesizes to parallel logic. When we implement this decode function, now built with a case statement, the result is fewer levels of logic and better speed. Note that we still use a default statement. This is an important basic HDL coding style to use whenever you build a combinatorial process. This helps you to avoid inferring latches, so to be sure you don't, use a default. Usually synthesis tools will warn you if you happen to forget the use of the default statement. So here are a few things you should remember about coding for the carry logic resources. Be sure to use the proper arithmetic operator to infer carry logic. Don't plan on getting carry logic if you define gates, such as the XOR gate. Consider other counter implementations, especially when you have a timing critical path that goes through an arithmetic function. Okay? And as we mentioned, some of the alternatives include one-hot, and that's probably one of the most commonly used ones, as well as Johnson and LFSR. They'll take extra time to construct, but might save some resources and improve the speed of your design. Consider using and/or carry logic for decode logic. This will take extra time to construct, but will run faster than a LUT implementation because it will take advantage of the carry chain. Use case statements for decode logic. This will simplify the decoding, saves LUTs, and improves speed. And really the most key thing is improved speeds by tending to synthesize to more parallel logic. And for best density, try to use carry logic in pairs or in an even number of bits.